Homework 36, page 368, section 6.3, numbers 1 through 19 odd, 37 through 45 odd. Okay, so that's your assignment for the break. Along with, I'm going to email you a quiz. If I don't, I got a lot going on today. If I don't email you the quiz, text or email me when you notice I'm waiting on a quiz. But I should have it to you soon. Although today's going to be crazy. So anyway, all right. So we have a problem. Find the volume obtained by rotating the region. Gives you region. Oh, yeah, no, that's right. About the x-axis. This is nothing new. This is exactly what we did last time. This type of thing. So what's the first thing I want to do to get to this?
Graph it.
I want to graph it, right? I'm going to graph the region. So first off, let me come right over here.
It's like
So, all right. So sine is one of them. Okay, I'll start with sine. There's sine, and it keeps going forever and ever. Okay. But y is 0, so that's the x-axis. Okay, x is pi, so here's pi, and x is 2 pi. So if I imagine, I'm intersecting these planes, I have pi, I have 2 pi, I have x equals 0, or y equals 0, sorry, and then I have this part here. So the part that's bounded by all those regions must be that part right there, right? So this is the region I'm trying to find. And because that's the case, I'm going to go ahead and get rid of this right there. Okay, there's that. Now we're rotating this about the x-axis, right? So this thing gets flipped up like this. Okay, and what we're doing is we're rotating it around like this, right there, right? There's the back. Okay, so we're just going to chop this out. This is the same thing we did last time. So this is just review, right? I'm going to take one of these representative things here at x. Okay, at x the height is here, right? And so I'm going to make this washer right here, or a disc. This, by the way, I don't know if I said it explicitly. I'm going to call this in this class, this is going to be called the disc method. Okay? It's the disc method of finding a volume of revolution. Okay, so so now I've chopped this into n pieces, this way, right? And now I want to find the ith volume. This is the ith because this is xi, right? I want to find the ith volume, and the volume is a what times a what? Area times the length, and the length that we're going to use here is going to be delta x. Yeah?
yes.
Okay, so area times the length. Now that area is the area of this face right here, right? Because we have our, use colors this time, our delta x is this length right there. It's the width of the disc. And the area, AI, is the surface area of this object, right here, right now. And the surface area, that thing is a circle, because we just took a line, or a radius here, and we revolved it around the x-axis. It's not changing, so it's a perfect circle. It doesn't look like that, because I'm drawing it in 2D. But it's a perfect circle. And so it has its area is of the form what? Pi r squared. And the only question is what's r? Now in this case, if I plug r, if I use just the value of the function itself, sine x, we get a negative number. That doesn't matter because I'm going to square it, right?
Yeah.
Like it's the same thing as if I could just say r is this part up here. Right, which is negative sine, but I know I'm going to square it, so it's not going to matter. So I'm just going to go ahead and say, I could go negative sine x squared delta x. but it's negative squared, so it's just going to be positive. It'll be easier. I mean, it's one less symbol to write, but really it doesn't matter.
Yeah.
So, okay, anyway, so that's the ith volume. And when I add all those up and take the limit as delta x goes to 0, or as n goes to infinity, whatever, we get an integral. What integral is that?
From pi to 2pi.
From pi to 2 pi of pi sine squared dx. There we go. So let's do this real quick. So there was my work. All right, so I'm going to pull out the constant. And now we have sine squared. How do you want to write sine squared?
Well, you could use substitution. You can just do
You could.
sine times. Oh wait, no, it's just.
It's not going
We
to
don't
work.
really.
So sine squared is the same thing as 1 minus cosine squared.
Oh yeah.
Which, okay. But from that, we could get that this is the same thing as 1 minus 1/2 plus 1/2 cosine 2x.
Yeah.
Which is the same thing as 1/2 minus 1/2 cosine 2x. All right, when you have one trig function squared, this is the probably the most straightforward way of doing it. Or you could just have locked in your head, like I said back in trig, whenever you see this, just do this. Like this is a good one to just have in your pocket. Okay? So, okay, what's the antiderivative of this? So we have pi
1/2 x
1/2 x
minus 1/2 sine. That would be
1/2 sine 2x, but there's a 2 that would have get multiplied, so he would have to have come down.
Yeah.
And we should get 1/4 sine 2x. Now let's take the derivative and make sure. Take the derivative of that, you get a half. Take the derivative of this. Okay, sine goes to positive cosine, so you'll have cosine 2x. So 1/4 cosine
Times
2x times the derivative of the inside stuff, which is just 2, and that works back out to that.
Yeah.
The sign is correct, the SIGN is correct. So we're good. Okay, so now let's evaluate that guy up at 2 pi and down at pi, and we get the pi on the outside. Now, plugging in my 2 pi gives me 1/2 times 2 pi is just pi. Minus, that's an integer multiple of pi inside sine. So it's a
zero,
big
zero.
fat 0. Minus, okay, I plug in my 1 pi into here and I get my pi over 2. Minus, again, integer multiple of pi. That's nice. So I get,
minus pi over 2. So just pi over 2.
pi minus
times
pi
pi,
over
yeah.
2. Yeah, times the pi. Don't forget that is pi over 2.
So it's just
Pi squared over 2. Is that what I got? Yes. Good. Okay. Okay. Good. So that's just a review. That's just a review. That's all that is. Now, same question. The only difference here. The only difference. Uh-oh. Same region, but now we're going to rotate it around. This way. Okay, so let's get rid of half of this and just look at the thing itself. Which is, okay, now here's the thing. When I did this way when I went to do this. I went, okay, let's just look at this half.
Like the top half.
Yeah, just the top half.
That was.
It's actually the bottom half, right? That we care about?
Yeah.
Yeah. But we're computing a volume, aren't we?
So it doesn't matter.
Yeah.
It doesn't matter. But there's I want to do it this way just so that at the end. Now, I don't suggest you do it this way. This is the way I messed up. Okay? And it's not a big deal, but I think it could be instructive if you do it this way. So you think to yourself, well, it's an area. Like, it's just like with you're trying to find the area of something and you know it's going to be positive. It doesn't matter, right? The same way the volume's going to be positive, so it doesn't matter if you use the top or the bottom.
Yeah.
Is that going to mess you guys up if I do this?
I don't think so.
let's just do it the right way, okay? Like, we'll still have the same conversation at the end. We'll still have the exact same conversation at the end. But let's just do it the right way. So, comes up, comes down, and this is the thing that we're doing. So this is the region as defined. Right there, it's that right there. And now we're rotating it about the y-axis this way. Okay, so this is the thing that we want. It goes down to negative pi, negative 2 pi. It goes down to here, like that. So we're rotating this thing around like that. And we're getting this kind of cup thing. Everybody see that?
Yeah.
Right? That's the thing that we're rotating around. Now, what we'd have to do is say, well, hold up. Okay, x, y. Like if this were in your homework set, this is what you would have done. You would have said, okay, let's reinterpret this guy. Now, here's my y. Here's my x. From 2 pi down to pi goes like this. And then from negative pi down to negative 2 pi, he does this. That'll be useful. But that's 1, because we're going to be integrating across here, so we'll need to know. And indeed, or oh, it's negative. See, this is what I just pretend now that this is what we have. It's the same thing, right?
Yeah.
And this is what I did earlier. I popped them up, and I said, it's the same thing. Who cares? And it really, who cares? But you just have to be careful in the end. And that's what we're going to talk about. But anyway, so we'd reinterpret it this way, and we'd say, okay, now we're going to rotate this guy around like this. And so we have a big volume, right?
Yeah.
Your big volume is given by this part that's been rotated around. Okay, so like that. I'm going to call this volume big. And we're going to subtract off the inner volume, volume small, like this. That's what you get when you rotate that guy around, right?
Yes.
Volume small. And so you say, okay, now,
Oh, okay.
right?
Yeah.
Now I just need these functions. I need to know what function that is. And so you go, okay, y equals sine x. And so arc sine y equals x, right?
Yeah.
Uh-oh. Uh-oh. These are different parts of arc sine. And they're not where they should be. Right? Arc sine does this.
Yeah.
And this. And he goes through here at 0. So what you could do is say, okay then, this, and we remember this has been shifted up to pi. So you could say, okay, so this thing is this branch. He's been shifted up to pi. So this thing must be arc sine y, but just shifted up. So arc sine y plus pi.
Wait, arc sine. That's how you would shift it up. Oh yeah. Yeah.
Right, hold up, and let's make sure that I've done this right. Inputs are y, because I flipped this around. Inputs are y, outputs are x's. That's what I did here. I took the inverse, so now inputs become outputs and vice versa. And now it's just that, oh yeah, it's not like sine in the first part. This is when sine goes between pi over 2 and negative pi over 2. We want it over here between pi and 2 pi. So I'm going to have to play some stupid game where I say, well, I guess you're just adding pi to shift that up. Then this guy, this is going to be the hard part because that's that part. So I'm going to have to take him, if this is arc sine y, I guess I'm going to have to
Wait,
shift.
that's that.
What now?
Oh, it's that part negative.
Say what?
They're curving different ways, right?
Well, they're symmetric. So, I mean, this is the same thing as this,
Oh, okay.
I think.
just negative.
You
right?
see, well, as you can see, this is already getting really hairy. Like, you know. But let's just imagine what we have to do. This. Oh, yeah. Oh boy, I think I see what you're saying. Is that the same thing? Who cares? Because this isn't the way we're gonna do it. So, but I just want to show you what you'd have to do. I guess what you could do. Well, let's just call this negative arc sine, so that he comes down like that, and then we'll shift him up by 2 pi. Okay, so 2 pi minus arc sine y, something like that. I think that should work.
Yeah.
That should work. Okay, so here are your functions. Those are your functions, and now you need to find their volume. And so you do the pi times this thing squared, and now you're integrating pi times 2 pi minus arc sine y squared dx, and then you're going to subtract off. Thank you. Pi, this thing, which is arc sine y plus pi squared dy. When you square that out, you're going to have something with like 4 pi arc sine y and an arc sine squared.
And something else.
Do you know how to integrate either of those? I mean, this is tough, but it's doable. Good luck. I mean, probably integration by parts.
Yeah, that's
Oh yeah, because it's arc sine times. Yeah, you can do.
Right. You probably something like that, or u substitution here. You'd have u squared. Du would be like 1 over root 1 minus u. And so you'd have u squared, and then you'd be multiplying by that. But then you'd be multiplying something like this. You'd be integrating something like this. 1 minus u squared du. Probably a trig substitution. Probably, and then you do your trig substitution, and you end up with, I think it's something like this. Cosine u. And so now you do your other, so actually it's not that, it works out to finally, the thing that you're integrating is this.
Okay.
Integration by parts twice, right? To get this guy down, because, right, if you're integrating x
Oh yeah.
cosine
Do it
x,
twice.
you do your u is x squared, du gives you your 2x, your dv and blah 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 blah, and so then you do that. And then you got to do it again because now you're only down to x sine x, and so you got to do another integration by parts. Why? My point is, this is wicked hard. This is not the way. You might ask yourself, is there a better way? There is a better way, and that's what we're going to talk about today. Okay, and what we're going to do. You see, the thing is with these types of problems, you don't know whether you should use the method that we did last time, the method of disks, or what we're going to do today, which is called the method of cylindrical shells. And usually what it is if you almost always do the method of disks. You think, oh, I'm going to try disks. And then when your integral gets crazy, because you've taken the inverse of some function and you're like, oh god, oh no, this is bad. Then think, oh wait, cylindrical shells. What we're going to do is say, this is the volume I want to compute. And so we could chop this up right here. We're going to chop up this volume the same way we did before and say, okay, we're going to chop it into little pieces a length of delta x.
Oh, we're dropping delta. Wait. Oh wait, never mind.
Right? Because this is the solid thing. The solid thing is like a donut, right?
Yeah.
And I didn't draw back behind. It goes behind him like this. But this is the type of thing that we're getting here. And it comes down like this. It's a cup, right? Right?
yeah.
That's back behind it, you can't see it. It goes like that, and that's a little back like that. That's the volume that we want to chop up. Chopping them up this way is not a good idea. As we've just seen, because we could need to integrate arc sine squared. No fun. So this is what we're going to do. Here's another way of chopping this up. I'm going to just look at the cross section here and take this rectangle Boom. That rectangle right here, which occurs at some value on the x-axis, we will call it x. Okay, so you plug in your x, you get out your value, that's the length of the thing. And the width of that rectangle is delta x. Now what we're going to do is take that little rectangle and we're going to revolve him around the y-axis, like this. And that gives us a volume of something. Like this. This is called a cylindrical shell. And what we're doing is the method of cylindrical shells. And so, there's your thing. So let's try to find its volume. This is the ith volume right here. And if it's a cylinder, so hold up just a second now. Here's the thing. There's your thing. This is the ith volume of your beast. And as you can see, right, as those get smaller, the sum of these things will be the volume. Does everybody see that?
Yeah.
Right? Because what we're doing, we're taking all of the little cylindrical shells, right? This little cylindrical shell, this one, all of them all the way out to there. Then we're letting them get infinitely thin. And when they do, it should converge to the volume that we want. So what's the volume of that? Wait a minute. First off, what is a volume? Is a what?
Area times the length.
It's an area
So it would be
times a length. And let's call it L, length. Okay?
okay.
Now, here's the thing.
Well, the length is delta.
That's what I'm thinking, right? And so here's the area that I'm looking at is going to be the surface area of this thing. Right? And let's just think about this. Let's just take the outermost part of that. Okay, so we just have the outermost thing. It has no width, or it has no depth, right? It's just a piece of paper that we've rolled onto itself, right? Like that. Now what I'm going to do is cut it right here. Cut it in half. And now let's open it up. So this is what we're doing to this thing, right? We're opening this thing up until finally it's just one big flat. What would that be? What shape is that?
Just a rectangle.
It's a rectangle. What's the area of a rectangle?
Length
Length
times.
times the length.
Okay, so let's call it the height times the base.
Okay.
Just so, because we have a lot of I's and L's and blah, blah, blah. So, okay, H is what?
Delta x.
No.
H is that
Negative
part.
one.
Look back there.
It's 1.
Oh yeah.
Well, but not at X. What if X were over here?
Oh, it's just sine of x.
Yeah.
Yeah.
Right? It had better be. X had better change. It's not always 1. I've drawn it there, but you know, it depends on what X is. So, H is whatever the function is at X, f of X. In this case, sine X. Yeah?
Yeah.
Okay. What about the base? What shape is this if we were to look at it, down at it like
A
this?
circle.
It's a circle.
So the circumference.
It's the circumference of the circle. So what's the formula for circumference of a circle?
2 pi r.
2 pi r. Okay. So 2 pi r. What's r in this case?
It's
Sine of x.
No, it's
No, because it's
Look down at the thing. The r should be from here out to here. R. Right?
yeah.
Of that circle right there.
So it's 2 pi.
From the center,
yeah, it'd be 2 pi. Right?
well, that would be that outermost shell
Oh,
would be 2 pi.
but
The innermost shell would be pi, but we're not at those. We're at x.
So
so it's
pi plus sine of x, right?
What's the distance? Because we're at this one.
Oh.
Just X.
It's just x. Yeah. Oh man, it's tricky, but you can see the idea, right? X is however far out you've gone. That's how far you're going around, right? You're at some distance x. That's the distance, and now you're just flipping it around. So this is 2 pi x. So the area. Here we go. Here we go. The area was the circumference, right? The circumference of the thing times the height. And now we have, and we'll fill these in a second. Now, what's the thickness of the thing?
Just
Yeah. Delta X.
That's delta x. That's delta x right there. Okay. So we have the area, which is the outside, and delta x, which is the thickness. An area times a thickness is a volume, or an area times a length is a volume. So we got it. The circumference then was 2 pi x, in this case sine of x, delta x.
Yeah. We're just taking it.
And in general, this would be f, right? But we're going and you notice I didn't like write a general formula last time. I could have said if you have f and you're rotating it around a thing, it's this. I could have said that. But how many problems did you have in your homework where f wasn't the thing that you were rotating around, right? Oftentimes it was like, here's f, but you're rotating it around, say, this line. Well, then it wasn't f. You don't just plug in f, because plugging in f gives you this. But if you're rotating it around here, you need to find the radius from here to here. And that's why I do it this way. And I don't have this in my head. I start with a volume is an area times a length. How do we find that? And then derive it, and that's what you end up at. So, right, I'm also not, I could right now say, okay, 2 pi x f of x delta x, or dx, that's what you want to do here, but it's not always f. In this case, it happens to be just f. But we'll see in a minute, that's, if you have that locked in your head, your life's going to be rough. I think it's much easier to look at the shell itself, find a representative sample of it at some value x in your domain, draw the shell, or maybe you don't necessarily need to draw the shell, but if you do this, and think, okay, what's that, it helps if you draw the shell. It really helps if you draw the shell. And then remember, okay, the area is the outermost thing, that's a circumference times a height, and then the width of the shell is the delta x, and so boom, circumference, height, delta x. Circumference is always this guy. Almost always. I mean, if you're doing it on a different, whatever, okay? That's what's going to give you problems if you memorize that as, oh, that's f of x. Maybe. In this case, he happens to be f of x. So, okay, let's do this one. Yeah, this. Okay, so there's my ith volume. What's the integral I want to give me the actual volume? From where to where?
Pi to 2 pi.
From pi to 2 pi. Yes.
Of 2 pi x sine of x.
2 pi x sine x. Much easier than the other way. Because this is just 2 pi integral x sine x dx. What method do you want to use for this guy?
Parts.
Parts. So I'm going to let u equal what and dv equal what?
U is x.
Yeah. Which makes du what?
Something.
1.
Oh, du is.
Dx.
Yeah.
And dv is everything else. So that's sine x dx. Which makes v what?
Negative.
Negative. Don't mess that up. Okay. So I have 2 pi times uv minus the integral of v du. UV is x sine x. No,
Wait, x negative
no,
x
no.
cos-
UV.
Negative x cosine.
X minus cosine.
Did I do my integration by parts wrong? No, I did it right. Okay. UV, there we go, right? X, so negative x cosine x minus the integral of v du, that negative comes out and makes this a positive, and we get cosine x dx.
And that's all from pi.
And so 2 pi, I can get rid of this. Negative x cosine x. The antiderivative of cosine is positive sine. Now I evaluate those up at 2 pi and down at pi. And I get, okay, so 2 pi times. Plugging in a 2 pi into here gives me a negative 2 pi. 2 pi into here gives me a what?
Negative 1. No, 1.
No, 1.
Positive 1. Yeah, so positive, so I'm not going to bother with that. Plus, plugging in a 2 pi here gives me what?
Zero.
0. Nice. So there's the first part. Minus off. Okay, plugging in a pi here gives me a negative pi. And plugging in a pi here gives me
Negative 1.
negative 1. So it's negative negative, so I'm going to make it positive.
Plus 0.
Plus 0. Nice. So that's on the outside 2 pi. On the inside we have negative 2 pi minus pi.
Negative.
So
Oh, yeah.
negative 3 pi.
Negative 3 pi. And we get
6 pi.
negative 6.
Negative area.
Negative 6
Isn't it just 2 pi?
pi squared.
Yeah, pi squared. Is that
Why is it?
And we got a negative
Yeah.
volume.
what we. Wait, what?
But it was a negative area, wasn't it? So this is going to happen. And you're going to get to the end and you're going to go, uh-oh. Uh-oh. My area is negative. Look back and ask yourself, did you have a negative area?
Yeah.
Yeah, it's the area beneath the curve. So I could say, okay, hold up. Make sure I did all of this right. Right? And I did, okay? And so I expect, because of the way I set this up, I expect that if I take a negative number, right, and multiply it, do something, I should get a negative number. So that's what I expect. So, but the volume, we're going to say, I mean, you could say it's the signed volume. There is that. Same way we have a signed area, area above the curve is positive, area below the curve is negative. Ditto here. Although, since we're thinking about it as a volume, just abstractly, just somewhere in space, we'll just say it's positive. However, here's the thing. Don't get in the habit of getting a negative number and going, oh, right, but it's positive, so it's positive. What could have happened, you do your integral, and if you do your integral of whatever it is, from there to there, and you get something like this, 1/4 x cubed minus 2x squared minus x, and you're evaluating that guy from like 5 down to negative 2. There's a lot of crazy negatives and plussing and minusing that might go wrong, okay? So you need to stop and let's say you get something that's like negative 36. You need to stop and go, hold up. Did my original picture have a negative area in it? Did it look like that and that's the thing I was revolving around? Because if that's the case, it looks like we got a lot of negative area here. The total area down there, it should be a negative area. So it should give me that, right?
Yeah.
But if you did something like this, and your original function was, I don't know, something like that, and you're going from here to here, and that was your original area, hold up, not so fast. Maybe in this case I mixed up some signs, like when I plugged in that negative 2, am I sure that when I made that negative that it was negative?
Yeah.
You know what I mean, right? There's a lot of places you could mess up on this. So my point in all of this is you might end up with a negative area. When that happens, stop and go, did I mess this part up? And if you didn't, okay, then let's just make sure, like in this case I got a negative area, is that what or negative volume, is that what I expect? Yeah, that's what I expect, because this entire area was negative. And when you compute the integral of it, it should give you a negative number. But now we just know like what we're talking about. What you could do is just do this, but that's a pain, right? I think it's much easier to just say, hold up, let's get to the end here. Yeah, okay, no, this makes sense. And after making sure that you did this part, this minus the other thing, as long as you did that right, then you can be confident, like, yeah, okay, now we'll just make it positive here at the end. I didn't look at the answers in the back of the book. They may very well have negative volumes. I don't know. Anyway, so that's that. This is the method of cylindrical shells. Last time, we did the method of disks. The disk method, as I call it in your quiz. Okay? So let's look at another one of these bad boys. All right. Okay. This is number 12. Use cylindrical shells to find the volume of the region rotated about the x-axis. So here's number 12. Rotate about x-axis. And it gives you the region is defined by x equals 4y squared minus y cubed and x here. So it's the region bounded by this. Now what you could do is say, okay, hold up. All right, here's my x, here's my y. That's some kind of thing. Let's see, that's a y squared times 4 minus y. So that's some kind of something like this. Or you could say, hey, this is y is the input, right?
Yeah.
Right? So don't make this harder on yourself than it needs to be. Like 12 through something or whatever it is, I've lost my place, but there's some group between 1 and 19 that has all of them are like this. Y's are your inputs. Okay, well just make y the input variable.
Yeah.
Super easy. Like, don't make this harder on yourself than it needs to be. And we're rotating about the x-axis. About the x-axis. So this lends itself to a cylindrical shell very easily. So let's draw what this region is. It's bounded by x equals 0, so that's the y-axis. And this. Now, this is, this is third, what do we call this type of thing?
Polynomial.
It's a polynomial. And it's a what type of polynomial?
Or cubic.
Cubic, right? And so a cubic either goes up forever like this and down forever like this, or it's up forever like this, down forever like this. Which one? Does it go from high to low or low to high?
High to low, right?
High to low, because the highest order is cubed, right? I mean, that's not why, because it's negative. The cubed thing is a negative. So that means as this gets bigger and bigger and bigger, it's going to get more and more negative. Okay, so I'm looking at something that looks like this. Now, do we have any zeros of this guy? Where do the zeros go?
1
Through 0, which is the worst.
At 0 and where?
Negative 4. Negative root squared cube root of 4. Wait, no, negative.
What number do I need to plug
just
into
4.
y to just
Sorry.
4? Yeah, that's cool.
Yeah.
That's cool. Okay, so he must go up. Does he cross through here?
Yeah, he crosses.
He crosses through because that's to an odd power, right? And then he comes down. He must come down and touch. Does he bounce?
Yes.
Yes, because he's an even power, and so it looks like that. Okay, so he comes down, touches, and does something like that. And because it's not a parabola, I mean, it doesn't matter how you draw this. It just happens to be that he's going to hug a little bit longer, because he looks more like y squared there. So,
Oh, yeah.
I mean, its derivative is flatter there. Yeah. Anyway, here's the thing. Okay, here we go. So from 0 up to 4 is what we care about. So that's the thing right there. And we're rotating it about the x-axis.
Wait, how do we know it's just from 0 up to 4?
Because it's bounded by this. We have a curve bounded by a line, and everything else is infinite.
Oh, okay. Yeah.
Right? Right, like all of the other, well, it pops back up. So from here to here would be infinite.
Oh, okay.
From there to there would be infinite. So the only one that they could be talking about is the thing that's entirely enclosed.
Yeah.
So this is the area. Cylindrical shells is going to make the most sense here. Now, what we could do, good luck, if you thought, okay, well, I'm rotating it around, so let's do something like this. Let's try the disk method. And you do that. And so you go, okay, here's the disk method. It does this. Okay, outermost. Now you're going to have to find the top half of this guy. Y equals x. How are you going to do that? How would you do that? How do you solve for y in terms of x with a cubic? You could do it with a parabola, but with a cubic,
Binomials.
good luck, right? However, so this is the kind of thing. We're trying to find this volume. One of the first things you might think is, okay, disks. Let's do disks. And we'll flip this guy up so that he does this. Uh-oh. So I'm going to need a big volume and a little volume. So I'm going to need this branch, y equals what? And I'm going to need this branch, y equals what? Uh-oh. I don't know how to take the inverse of a cubic. So maybe this isn't the best way to go. Maybe I won't do that. And of course, in this section, everything you're doing is cylindrical shells. And it even tells you, use the method of cylindrical shells. So I'm going to draw what that would look like. He's going to come around like this, back up, boom, like that. One of those cylindrical shells is going to look like this. Right, so it's something like that. And here we are at some value, call it y. Okay, so my representative cylindrical shell has some volume. And a volume is a what times a what? An area times a length. And in this case, what's the length that we're looking for? What is that thickness right
Delta
there?
X.
Delta, is it x?
Delta y.
Delta y. There we go. Okay. Area is then the surface area of this thing, which is
A circumference
the
times height.
circumference times the height. The circumference times the height. So, I'm going to write that circumference times height, delta y. So the circumference is what?
2 pi times r.
2 pi r. Okay, so circumference is 2 pi r, and what is r in this case?
Just f of x, or the function.
Function's there. R is here.
Oh, just y.
Yeah, well,
Yeah, y is r in this case. Careful with that. 2 pi y, and h is what?
That's
That's f of x, or
f of
x of y,
Yeah.
which is this guy. And since I'm about to do an integral, I think this way is going to be a simpler way of writing it. 4y squared minus y cubed delta y. Do we have everything?
Yeah.
I think so. So then the actual volume that we're looking for is what we get when we add up all the little volumes and take the limit as delta y goes to 0, and we get the integral from where to where?
0 to 4.
0 to 4, because each one of these little shells has to be accounted for, right? Every single one of them. So y has to take on all of these values, so we're going from 0 up to 4 of what?
Delta 2 pi.
Yeah, 2 pi comes out.
And
y times.
yeah, just
Y
4y
times that
cubed
stuff.
minus y.
There you go. That's how I would do it. 4y. You go ahead and distribute this y
minus y to
in.
the 4th.
Minus y to the 4th dy. And that gives me 2 pi times what?
It's 4 times
Fourth,
4th.
fourth,
So
so just
1 y to the
y to the
4th.
fourth.
y to the fourth
Minus 1
minus 1/5 y to the fifth, and I'm plugging it in up at 4, down at 0. Nice thing about 0 is going to go away, so I only need to worry about the 4. So I get 4 to the 4th.
But it's all negative.
No, it's not.
Oh no, because the 4 was first, yeah.
4 to the 5th. Because 5 is bigger than 4. And 4 to the 5th over 4 is bigger than 4 to the 5th over 5. Yeah, I thought that too. I was like, uh-oh, 4 to the 5th is way bigger than 4 to the 4th. But that fraction is smaller. So it will work out to be positive. And if you work this out, you get 2 pi times 256 fifths, which works out to 512 pi over 5, which is positive. Should we have expected something positive?
Yes.
Yeah, because this area was positive. Now, if it were down here, that would have been a different case, but it's not, so I feel good about this. I checked it in Wolfram Alpha and we're good. Everybody good on that?
Yes.
Okay, one more, and this is what I was talking about earlier. This is why I don't have a formula for it. The book has a formula for it, and I've found over and over again, students come to me and they're like, what is wrong with this integral? Why don't I get the right answer? And what I find is that they've written something like this down, and then they have whatever the function, it's given like this, f of x equals like root 1 minus x squared. And there's some region, and they've plugged this into there, and they've done the thing, and it's like, well, that wasn't the region. It said that it was bounded by f of x. What would that look like? That's this, isn't it?
Yeah. Wait. It's negative x squared. Oh, wait.
Root
Oh,
1 minus x squared. Yeah, because if
Yeah,
x
yeah.
squared plus y squared equals 1, then y squared is 1 minus x squared. So then you take the, 1 minus x squared root. So it's the top half, right? And then it's like, they've done something like this, because it's revolved around something. But it's not that. It's the actual region is the region bounded from there to 1 or something. And so this is the region that they're supposed to do. And so the actual height of their cylindrical shell was from here to here, right? Right? And so it would be, then the height would be 1 minus this thing. But you don't need to worry about that if you keep this out of your mind. Don't worry about that. Think about the method. How do you go about breaking something up into a cylindrical shell? What's the volume of the cylindrical shell? Add those up and that's an integral. So here's an example of that. We have a region defined by y equals x minus 2 squared plus 1 and y equals 2. It's the region bounded by those two objects. And I want to graph it. And so, so I'm going to graph it. And I notice that if y equals x squared, I have this thing. And if y equals x minus 2 squared, I have this thing. Because I paid attention in Algebra 2. And then I say, well, then if I do y equals x minus 2 squared plus 1, that just shifts everybody up from 2 up to 1. And you notice how I didn't like use a formula like, oh, that's h and a k, and so the vertex shifts to hk. No, it's just this is this thing, and it does this. And so, okay, goes here at 2 is its vertex at 1, and it goes up, and we're only going up to 2, right? The other thing that's bounding us is the line y equals 2. And I noticed that also, this goes up to 1 here at -1 and 1.
Yeah.
And so when I shift it over 2 units, it goes up to 1. It goes up, as I go over 1, it goes up 1. So when I go to -1, or I'm sorry, +1, it should touch at 2. When I go over 3, it should go up by 1 unit right there.
Yeah.
There are a lot of ways of getting this.
Yeah.
I made this example, so it works out nice. Okay, and now I'm going to double check that. Plug in a 3. 3 minus 2 is 1. Squared is 1. Plus 1 gives you 2. 1 minus 2 is -1. Squared is 1. Plus 1 is 2. We're good. Okay, so now take that region about, revolve it about the y-axis. Okay, so we're going to take this region and we're going to revolve it this way, like that. And it's going to come down here like that, back like that, back like that, okay, and forward, right? And now we could see, okay, I could take from here to here and chop that up. Take one of the x's as my representative x, and we go boom, like that. Delta x is like that. So we get a little rectangle. Now that's the rectangle I'm going to bring around as my representative right here. Right? Everybody get that? And so the thing that I have is this. Looks like that. He has some width this way. What's his width that way? Or his thickness?
Delta x.
Delta x.
Delta y.
Okay, so that's my ith volume. And a volume has the form of what times a what?
Area times length.
Area times a length. And that length is delta x, the thickness.
Area.
Now that area is what?
Height times circumference.
Its height, so the circumference times the height, delta x. What's the circumference of this circle?
2 pi r, and r is just
R
x.
is
Right, so the circumference is 2 pi r, and the r in this case is x, right there. So x is the total length right there. So 2 pi x. And what's the height?
2 minus.
Yeah,
1.
good, right? If you just plug, and now you could see what I mean. If you said, oh, cylindrical shells is this. Cylindrical shells, that's a cylindrical shell. So I'm going to go 2 pi x. F of x in this case is my x minus 2 squared plus 1 dx. What you've just calculated was the height from here to here, right? This would be the cylindrical shell you'd get if you had done this bit right there. That is that height right there, yeah? And so it would be the bottom of this thing if you'd done that. That's not what we're interested in. So let's find the height. H is this bit right there. So H is from here to here. How do we get that? I think you just said it.
2 minus.
2 minus
2 squared plus
the stuff,
Yeah.
right? The big thing minus the smaller thing. The smaller thing is x minus 2 squared plus 1. We can work this out. That's 2 minus 1 is 1. That's a minus x minus 2 squared. Yeah? So, okay.
Just take it.
Yeah.
So, this is the circumference, which is 2 pi x. The height, which worked out to be 1 minus x minus 2 squared. Delta x is my ith volume. Therefore, the full volume is the integral from where to where?
1 to 3.
1 to 3.
Pull the 2 pi out.
Pull the 2 pi out. Let's do that. Okay.
X
That
minus
stuff.
X times.
X.
Or you
So, x minus, hold up. Let's go ahead and, because I'm about to do an integral, right? So let's go ahead and multiply this out. That's 1 minus, what do I get when I square that out? So that's x squared minus 4x plus 4. So 1 minus 4,
It's
negative 3, minus x squared plus 4x. So minus x squared plus 4x minus 3. Do I have everything? 2 pi x, this stuff, dx. There we go. Okay, almost there. Almost there, almost there.
multiplying that.
Yeah, multiply it.
Okay, so multiply that guy out. We get 2 pi integral of negative x cubed plus 4x squared minus 3x dx, which is 2 pi times what?
Negative 1/4 x to the 4th plus 4/3 x cubed
Good.
minus 3 halves x squared.
There we go. We evaluate him up at 3, down at 1. Now in your quiz, you're going to get to this point, and at the beginning of the thing, I say, like, you don't have to fully evaluate it, but I want to see you plug these points in. They're not as nice as 3 and 1. And the reason I'm telling you to kind of stop there is because...
Here or
No. So okay, hold up. We're not stopping yet. We're gonna. This is so on the quiz. This is what I'll be looking for. That you go 1/4, 3 to the 4th, plus 4/3, 3/3, minus 3 halves, 3 squared, minus 1/4, 1, plus 4/3, 1, minus 3 halves, and 1. That's where you stop, because the actual things that you're plugging in are ugly, and I don't want you to have to multiply them out. But you might want to check in Wolfram Alpha that when you do plug all that stuff in, that you get the same thing as when you plug your original integral into Wolfram Alpha to check, because you should all be checking your quizzes. Okay, so that's where you could stop on the quiz. And I'm telling you, it's not 1 and 3. Boy, it's ugly. Yeah, this works out to 16 pi over 3. This is what you do. Okay, so let's do the questions that you had. You said 51 and 57.
Yes.
So we want to find, we have a sphere of radius. Okay, any questions on this stuff? Okay. You cannot go wrong if you draw your stuff out. I mean, that's how I say to do it. Don't think of formulas. I mean, you're gonna have to remember some stuff, but I've seen more and more students fail by, not fail, I mean like, not succeed in the problem by just plugging things into a formula, you know? And so, this is number 51. And we want to find the volume of, given a sphere of radius r, we want the volume of the cap that has a length of h. I've drawn it like that to really mess you up. What I'm going to do is say, hold up, let's reorient this thing this way. We have a cap of depth, whatever, h. Since this is a sphere, he comes out to r. H then must be where on the x-axis? If I were to give that an r minus h. Okay, so that's at r minus h, right there. And now, that's the volume we're trying to find. So this looks like, to me, this looks like we have a function like that, and I want to take it and revolve it around like that. Okay? So this looks like a disk. Looks like I could use a disk method. as long as I'm just going from r minus h up to r. So what's the formula for this function?
X squared
plus
root x squared
Root what?
plus x squared
1 minus
plus r
x squared. Right? The square root of 1 minus x.
r squared plus
So
R minus
x squared plus y squared equals r squared for that guy.
Oh,
Right.
Yeah.
And
R
so
squared minus
r squared minus x squared. Okay, so root r squared minus x squared is that guy. Okay, so it's disk, this disk, we've chopped up the domain and we've taken the representative value at x, and so this is the ith volume. And a volume is a what?
area times
An area times a length, and in this case the depth of this is what?
delta x.
Delta x. And so the area of this disk, an area of any circle is what?
R squared.
Pi r squared delta x. R in this case is what?
Root r squared.
Yes, the root of the stuff. So pi times r squared. R is root r squared minus x squared. And so that conveniently,
It's just
now we don't have to deal with the thing. So there's my ith volume. And now if I add them all up, I get an integral. That integral goes from where to where?
R minus
R minus
h.
h.
R minus h up to r. And the thing I'm integrating is pi, so I'm going to pull him out, and then we have an r squared minus x squared dx.
Yeah.
So that gives me pi times antiderivative of that,
R squared x.
r squared x, because r is a constant. They gave us a constant. It's not a moving sphere, because that would be a much harder problem to solve. So minus what?
1/3 x to the 6 cubed.
1/3 x cubed. You could probably get a PhD solving that problem. R minus h. Okay. Yeah, let's do it. Okay. It's what you get when you plug those in and subtract them from each other. Let's just do it. Okay, so pi. Now, plugging in an r gives me, that's an r and that's an r squared, so r cubed
Minus 1/3 r cubed.
minus 1/3 r cubed minus r squared
Times
r minus h. So r squared times r minus h minus 1/3 r minus h cubed. R minus h cubed. That's kind of... Okay.
We
Alright,
factor
okay.
in
Now hold up.
Factor in an r cubed. First thing.
So,
That might
well,
help.
yeah, maybe. Hold on. This is how I want to do it. This is what I'm seeing. I'm seeing that's going to work out to an r cubed.
Oh, you could factor in r cubed from f. Oh wait, why is that an
Not
x?
there,
Yeah.
There we go. Okay, so hold up. I don't know if this is going to be better or worse, but this is what I see, and now that I've seen it, I gotta chase this rabbit. This is going to be minus r cubed. See, that's what I'm seeing. Minus r squared h. R squared h. Minus 1/3 times r squared minus 2rh plus h. Oh, shoot. Oh.
It's the cube.
Dude, it's that. I mean, like, it's cubed. It probably reduces down to something nifty, but we're done.
What does it say in the back?
51, let's find out. So
This
this
is
is
gonna be like
6-3.
2 times odds.
This is 6-3. Yeah, 2r each.
Yeah.
6-3, number 51. Or was this? No, 6-2, 51. 6-2, 51. Yeah. Pi h squared times r minus
Oh, yeah,
a
there's
cubed. I'm sorry. Yeah. Pi. Why did I just lose this? Where's 51? h squared. R minus 1/3 h. So yeah, that reduces. Yeah, sure. I'll believe it.
Yeah.
Yeah.
You'll get there eventually.
You'll get there. And you can see the r cube's gonna drop out. So you shouldn't have any r, or oh, that r cube drops out. Oh, and then you'll end up with a third of an r cubed here, which will make that drop out. Then you'll have some squared terms and stuff like
We
that.
can factor out the squared.
And yeah, it looks like
The h squared.
the rh squared would probably cancel the third whatever in there.
Oh.
You know, because, and yeah, so r minus h cubed is r cubed minus 3r squared h plus 3rh squared minus h cubed. And if you take a third of that, we're just gonna do it, okay, fine. Pi times r cubed minus 1/3 r cubed minus r cubed plus r squared h
Yeah.
plus r squared h plus 1/3 of this.
And all the threes go away. But yeah, everything cancels somehow.
Everything cancels out and you're left with that. Okay. Okay.
Except for
Since
the h
we're
squared.
coming towards the end, let's hurry up with this. So this is number 57. Still 364. Number 57. All right. It says the base of S. Saying, find the volume described by solid S. And it says the base of S is an elliptical region with boundary curve 9x squared plus 4y squared equals 36. So first off, before I even do it, if that's a base of something, I'm going to need to know what this thing looks like. And so I'm going to divide everybody by 36. There's a 6. There's a 1. 9 and 36 gives me what? 4. So 2 squared. 4 and 36 gives me 9, right?
Yeah. Yeah.
Right? 9. Y squared 3 squared.
So there's
There we
like
go.
up to -3 and -3.
So he's an ellipse that goes through at -2 and 2
Yeah.
and up at 3 and -3. Like,
We've done these now.
yeah, it has been a while. Okay, so that's the base of S right there. And let's just make sure when y is 0, you get that equation. 2 squared comes upstairs, and you get that x is plus or minus 2, which is what we see. When x is 0, we get y equals plus or minus 3. Y equals plus or minus 3. We're good. Okay, so now cross sections perpendicular to the x-axis are isosceles right triangles with hypotenuse in the base.
What does that mean?
Okay, so that's the base of this thing. So the base of it is like this. Right, we're imagining here we have an x and a y axis. So we have an x and a y axis. And here's my base of the thing.
Is the base at?
So the base is here. And now we're going to go up into the z direction.
Yeah.
So the base goes from 2 down to -2, up to 3, down to -3. And it says,
Okay.
cross sections perpendicular to the x-axis. So if you're perpendicular this way, right, are isosceles right
So the 1, 1,
triangles with the hypotenuse in the base. So right triangles with the hypotenuse in the base.
Oh.
So, from here to here, because it says cross sections perpendicular to the x-axis are isosceles. So that means that this length and this length are the same. So if this is 5, this is 5. If this
that's what
is
isosceles triangle.
yeah, isosceles. So A, and then hypotenuse.
Wait,
Okay.
Wait.
Yeah.
Oh, that's like the one.
The 1, 1, or 2.
Yeah.
Accepted.
And so when it's here and here, he comes up like this, and they're right, and they have the same length. When it's here and here, it's right. That's what you're looking at.
Oh, all of
Wait.
those triangles.
So
Okay.
there's. Oh.
And you have to
Oh,
find
I
like
see,
the
I see.
right. Wait.
And so we need. They already told us how to chop it up. We just need to know now that we've chopped up the x-axis.
So it's like a pyramid
Here's
with a circular base.
delta
Kind of.
x.
It's like a cone.
Yeah.
Uh huh.
Cone.
Yeah, yeah. And so let's take the ith one right here at x. That thing is this. Now the hard part is going to be finding the area of that guy. So the ith volume, let's just look at this. The ith volume is a thing that it has some length here, given by this minus this.
Right?
And then here's this. It's a right triangle.
Hypotenuse is 6, right?
Yeah, and
Yeah.
so the hypotenuse.
Oh no, that can't be 6. It's just
So
Since
it's
those are the same, let's just think about it this way. Here's A and A.
hypotenuse is.
We'll know that. Let's first find the
X.
area. Here's the area.
Well,
There's the
let's
ith
just-
area. Now, let's say that we've already found out what that
2x
length
squared.
is. And let's call that length, I don't want to call it y, let's call it L. Since that's a hypotenuse, then that squared plus that squared has to equal that squared. A squared plus A squared is equal to L squared. So that 2A squared is equal to L squared. So that
Square root.
L is root 2a squared.
L, well, we don't, no, we're not solving for L. Because remember, L we could find. This is L from here
Oh.
to here. That length is L.
Oh yeah, so we're just okay.
And so now I want to know, because, I'm sorry, and I didn't state this explicitly. Why am I doing that? Because I know that the area is equal to 1/2 the base times the height.
Yeah.
And if that's the case, I could just reorient this thing to be A times A,
Yeah.
right?
Okay.
And so, right?
Yeah.
So then the area here is going to be 1/2
A squared.
A squared. And so I know L. A squared is L squared over 2. Now I just need to find L squared. L squared, well, L is this right here, right?
Yeah. Just
And
So-
so
just-
we just need then
2 times.
2 times whatever this is going to give us. So here we go. All right. Whew. Well, they gave us this. I needed to do that in order to graph it, but now it's going to be easier if I just do this. Although, will it be? It'll give you the same thing. Watch what's going to happen, Justin. Squared. I'm trying to get that y by itself, and so I could have just left it.
Oh yeah.
And it's a square.
36 over 4.
Uh,
That looks right.
What? Yeah. Yeah, and because that's 3 squared over. Yeah, that works. So why don't I rewrite this? This will be a lot easier if I write it like this. Then I'm going to take the positive square root. That gives me 1/2 root 36 minus 9x squared.
Which is a square, Z.
Which again, and you see,
Oh,
this
yeah.
is why I would have done it this way. Like we had x squared over, what was it? Well, I guess 2 squared. Y squared over 3 squared equals 1. And now we could rearrange this to get 1 minus x squared over 2 squared, like that. Y squared over 3 squared. Y is 3 squared times 1 minus x squared over 2 squared. So it'll be much cleaner. Take the positive square root, and we get 3 times root 1 minus x over 2 all squared. Which you could pull that out, right? This is what we got here, 36 9x squared. And that would be your next step. Pull that guy out because you know he's a whatever. Pull out the 36. You get 9 over 36 x squared. Then
Oh, and then pull out the 4.
right. And then you have x squared over 4, which is x squared over 2 squared, which is x over 2 squared. So this is much cleaner to go down this route right there. Yeah? Much cleaner to do that. And so, okay, we've done that. That's y. But we don't care about y, we care about L. And I just erased it, didn't I? I said that L, if we know L, we know that a squared is equal to L squared over 2.
Yes.
And so what we're looking for is the ith area is going to be, a squared is L squared over 2. So now I need to find L. I know this part, so L must be 2 times whatever that part is.
Yeah.
So y is 3 root 1 minus x over 2 squared.
6
2 times it,
It's just 6 root.
2y is 6 root 1 minus x over 2 squared. And when that's L, yeah? Because if this is, I just want to make sure, that's y. So 2 of them is L. If that's y and that's y, then L is 2y. L is 2y. And we have that the ith area is 1/2 L squared. So that's 6 root stuff squared over 2. So that's 36 over 4 times 1 minus x over 2 squared. Woo! And now we need to integrate. So there's my ith area. An area times, so then the volume. So my ith area was, what's 36 quarters? 9. 9, 1 minus x over 2 quantity squared. So then my volume is my area times delta x, which is 9, 1 minus x over 2 squared, delta x. And so, the integral I want to compute is from where to where?
Negative 2 to 2.
Negative 2 to 2 in x. Okay, so integrate from negative 2 to 2 of all of the little volumes. Pull out the number. 1 minus x over 2 squared is the same thing as x squared over 4. Dx gives us 9 times. Antiderivative of this.
X 1/16.
No, 1/12.
Minus 1/12x cubed. Double check that. 3 drops down, kills that off, leaves a 4. Yep, okay. Up at 2 and negative 2. Alright, let's try it. So, we get 9 times. 2 minus, oh boy. What's that? 8/12?
Yeah. Which is 4.
Let's hold up. Minus, let's just try this. Minus 8/12. Minus,
Oh, it might.
yeah, it might.
Oh,
Negative, or it might double up. Either way.
Yeah.
So -2
Plus.
minus this gives me a plus 8/12, and yeah, so it's
Yeah.
going to double up. But minus, a positive minus a minus
That's it.
is positive 4 minus,
So it's
oh yeah, minus
minus
2 of them, minus 16/12.
Which is
Well, 16/12, that's
8/6.
easier. 8
4/3.
4/3. Are you sure about that? 4/3?
Yes.
Okay, I'll believe you. That's 9 times. So 4 is 12/3.
So 8/3.
4/3. That's 9 times 8/3. Wait, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yes, okay. That works. So 9 divided by 3 is 3.
oh 24.
3 times
Wait.
8. 3 times 8 is 24. Let's see what the book says. 57.
At least we got a whole number.
Yeah, isn't that crazy?
Well, it is 24 because it worked out. Usually, if you did something wrong, it doesn't work out nicely.
24! We got it. Yeah, right? Like, you hit 24.7. No. Yeah.
It did happen to me, where I was off by like so little, and it's like so confusing.
And is it so annoying? Yeah, that's a tough one. You might see something like this. It will not be this bad in your homework. I'm glad you brought this up because it very well may have to do with an ellipse. And what we just did will help you enormously with your, not your homework, your quiz.